So I'm going to talk today about control flow enforcement technology, a new technology introduced by Intel that aims to protect our vulnerabilities in the code from attackers and from hijacking our code. My name is Oren. I'm a member of LLVM compiler team in Intel, Israel. And since this technology is developed by Intel, then I have here a list of disclaimers. I'll start from the end, from the summary. I'm going to show here, talk about control flow enforcement technology, also known as CET. It introduces new hardware-based solution that tries to do CFI, control flow integrity mechanism. It uses two techniques, Shadowstack and Indirect branch tracking, also known IBT. Shadowstack protects from our ROP attacks. How many of you know what is a ROP attack? Okay, good. So we have a lot of security experts, so I feel safe. And we also have another technique called Indirect branch tracking that protects against drop and cop attacks. I'm going to talk briefly about ROP attack next. The new technology introduces very low overhead. It shows very competitive protection metric rates, and it has very low performance overhead. So the presentation will start with a motivation and an overview. Then I will switch to Shadowstack and talk a little bit about Shadowstack, and then about indirect branch tracking, and I will end up by doing an analysis and a summary. So, ROP attack. Let's start from this example. We have here a very strange function. It has a variable, local variable called CMD. It's of size of 32 bytes. We are using here a C library function called getS. This getS function is not a safe function. And as you can see, there's no boundary check here. And then there is this funky if statement that probably will never execute this instruction, right? Well, I'm going to show you how it is going to be executed. On the left side, we have the stack, the data stack. And the data stack has also parameters and control flow, both reside on it. So we have the return address, we can have the input arguments, the stack frame, and also the local variables, including CMD. So if you're a nice guy, a nice user, then the input buffer will be probably of size of 32 bytes, and it will be inserted into the stack right here. But if you're not such a nice guy, you can see that there is no boundary check here, and because this is not a safe function, then you can actually do a buffer overrun and overrun the stack. So what actually you can do is change the return address, and the return address will point to this function. By doing so, after you finish running this function, you hit the return, you go here, and you execute this instruction. You can even be more evil than that, and you can inject your own malicious code into the stack. Now that you have control on the stack, you can encode your evil function and put it inside your stack. And the return address will point to this function, and it will execute it. Now, this thing is not really possible now because there is a security mechanism called DEP. DEP is Data Execution Prevention. And you cannot execute from a segment that is writable. So you cannot really do that. However, you can do return-oriented programming, meaning you can use existing code snippets in the code, in the library code, and jump to them and return to them. So here's an example. We have multiple return addresses, and the return address calls this function, and another return address that calls this function, and when you get back, you call another function, and so on. This way, you can actually perform a Turing-complete program of your own based just on libc gadgets. Okay? This is also a bit problematic because there is a protection mechanism called ASLR that tries to randomize the layout of the libraries in the memory. By doing so, it is harder for you to know to which address you want to jump. But it was proven that it is vulnerable as well, so you can actually predict it. So ASLR, we still have a problem here. What makes it even worse is the fact that we have unintended gadgets. So I'm going to talk a little bit about unintended gadgets now. So Intel architecture allows instruction decoding to start from any byte. It does it because it has a variable length instructions. Okay? So if it was all instructions were 32 bytes, then you don't have any issue because you always start from an aligned address. But because the instruction length is variant, then you can jump to any place. So an attacker can scan the code and try to find meaningful snippets, also known gadgets. An attacker can execute these chained gadgets. It chains them together to create his own mean or evil program. Let's see an example. This encoding is decoded to a move instruction. However, if you try to decode it from the third byte, you get an add instruction and a return instruction. It's really easy to find gadget like this because you have the return instruction and it is encoded into C3. And if you look in the binary and you search for C3 and then you look backward, you'll try to find some meaningful gadget that you can use. So it is an issue. And this issue is not only for x86. It was proven that you can do Turing-complete attack also on ARM and PowerPC and Spark and so on. Another example, we have here an encoding that is decoded to 2 move instructions. However, if you decode it from the third byte, you get an add instruction and an indirect call to a register. Okay. So is it that critical? Microsoft presented in the RSA conference that over 95% of the attacks includes ROP attacks. So yes, it is an issue, and we need to find a way to protect against it. There are similar attacks to ROP attacks. Jump-oriented programming, also known as JOP. In each JOP block, it ends with a jump instruction, an indirect jump instruction. By the way, why indirect jump instruction? Because direct jump is not that vulnerable because the address is fixed, is hard-coded, so you cannot hack it. Okay? So only indirect jumps that use register or memory, they can be manipulated. Call-oriented programming, also known as COP. In this case, the gadget block ends with a call instruction. You can see in this graph a statistic that was made on libc. And in this case, you can see the intended and the unintended gadgets in libc library. The intended jumps, indirect jumps, is really, really low. It is hard to create a program, meaningful program, just from these gadgets. However, when you add up the unintended gadgets, then it's really easy to create your own program. Okay. So we have defenses against ROP, JOP, and COP attacks, and this is what we call control flow enforcement technology. The control flow integrity checks, it's a mechanism that has 2 principles. One, you need to return, you need to branch only to valid addresses, only to places where you are intending to jump to. And you always need to return to the call site. If you call a function, then you need to return to the instruction that is followed by this call. Intel control flow enforcement technology is a hardware-based solution. It introduces CPU instruction set extension to implement CFI. It has Shadowstack, as we talked about. It prevents ROP attacks, and it saves the control flow to Shadowstack. This is how it does it. We have the data stack, and we have the shadow stack. Shadowstack saves only the control flow, only the return addresses, while all the rest is still in the data stack. Indirect branch tracking, try to prevent drop and copy attacks. It allows branching only to valid addresses. So let's talk about protection number one, Shadowstack. It tries to protect from ROP, and it also eliminates the case of return address corruption on the stack. So Shadowstack, as I said, it has a different and separate stack that has only control flow in it. To this stack, we have a special register called Shadowstack pointer that points to the place where your current return address is. This register is not writable by the user. It is implicitly writable. When we have special instructions, control transfer instruction, then this register is being updated. Let's see an example. When we have a call instruction, the call instruction, in this example, we have try to call the address 2000. It will push into the data stack and into the shadow stack the return address, which is the next address after this call. When we return from this function, then we'll have the return instruction push from both of them the return address and check that they match. If they don't match, then we have here a problem. For example, if someone evil tried to do some stack corruption in this function, then this address will be corrupted. And when we return, we'll try to match those two addresses and see that they are not even. In that case, we will raise a new exception called control flow protection exception. Shadowstack introduces mean IPC loss of less than 2%. It means that it has a very low overhead. There are some cases where we actually want to manipulate the stack and change the return address. In these special cases, we have special instructions that we introduced by Shadowstack in order to handle those cases. I'm going to name a few. So set jump and long jump. Set and long jump are library functions, also built-in functions in LLVM. Set jump, what it does, it saves into this buffer the actual return address. And later on, if we'll use long jump to this function, then we jump back to this function, to this location. What will happen is that this function will never be executed because we are doing indirect jump from this place to the address that is saved inside this buffer. In this case, what long jump also needs to do, it needs to unwind the stack and update the return address and so on. So the compiler needs also to do the same for the Shadowstack. It needs to save the Shadowstack pointer into the jump buffer. It needs to increment the Shadowstack pointer to skip the frame that we just removed. So it has two instructions to do that. It's called read SSP and increase SSP. Read SSP reads the Shadowstack pointer, and the increase SSP just increases the Shadowstack pointer. Notice that we don't have decrement SSP, meaning you cannot return to old frames. You can only release frames. Something very similar can happen also in exception handling. For example, when you have C++ code and you have a try-catch block, in that case, you might have in the try block a function call that calls another function, it calls another function, it calls another function, and then somewhere in the call stack you have an exception, and you throw an exception. In that case, you need to unwind your stack and go back and to this catch block. So you need to unwind your call stack and you need to change the return address. We need to do the same in case of Shadowstack. C++ runtime library was updated in order to use indirect jump instead of a return and to unwind the call frames from the Shadowstack. Sorry. So context switching. For each privilege level, we have different Shadowstack. The operating system is the one that's responsible to create those Shadowstack. When we switch to a different data stack, we also switch to a different Shadowstack. And the operating system can save and restore the Shadowstack pointer for thread switching, and it has new instructions called save previous SSP and restore SSP in order to do that. Those instructions use token-based mechanism to create those Shadowstacks. Okay, next protection technique called indirect branch tracking. It tries to protect against jump and copy attacks. So in indirect branch tracking, we need to make sure that we jump indirectly back to a place where we intended to jump to. Okay? We have two new instructions for that, end branch 32 for 32-bit programs and end branch 64 for 64-bit programs. The end branch instruction is a nope in legacy architectures. So you can actually run this code on legacy architectures. And in case when you indirectly jump to another location and you don't encounter an end branch instruction, then an exception is raised. Let's see an example. In this example, we have a function that all it does, it just calls another function indirectly. It gets a function pointer and it calls this function pointer. And here we have just some function that get an integer and return a Boolean value. When we compile this code using IBT enabled, we get two new instructions that I highlighted here, end branch 64. Those end branch instructions are instrumented because now we have global functions. And those global functions can be jumped to indirectly from somewhere else. So in order to allow it, we add the end branch instruction at the beginning. Notice another thing here. We have here an indirect call. This indirect call is exactly this thing, okay? The calling an indirectly a function pointer. So what happens if we try to indirectly jump to an end branch instruction? Then we are good. Everything is okay. However, if we try to jump to another location that doesn't have end branch instruction, we have an exception. So end branch instruction is populated in two cases. One is global functions, and the other one is when an address was taken. We will see an example for that as well. There is a new attribute called no CF check, no control flow check, that is used for two things. One, you can add it in front of a function, this attribute, and then you know that you don't need to instrument this end branch instruction. Okay. Actually, you would like to minimize the number of end branch instructions that you instrument, because every end branch instruction is a landing pad for attacker. Every end branch instruction is a place where attacker can try to indirectly jump to. So you would like to minimize those cases. So that's why we introduced this no CF attribute. Another thing is sometimes you don't want to instrument the end branch instruction. For example, in cases where you know that this jump is okay, is safe. The index is checked, the targets are checked, everything is okay. You don't need to add the end branch instructions. So in that case, we can add the no track prefix, and the CPU state machine will not look for the end branch instruction after the indirect branch. I'll show you an example of that. So in order to do fine-tuning of indirect branch tracking, we have the no track prefix. In this case, we have a function that has a switch, and we have a use switch, many cases. Okay? So think about it. For every case like that, we will need to instrument an end branch instruction. Okay? So we'll have a lot of end branch instruction. So again, it increments the code size. We don't want that. And we also don't want the attacker to have many end branches and many landing pads. Now it can jump to those locations. And so we would like to minimize those cases. Also, if you look at this assembly, let's take a look on it. This indirect jump uses a jump table and an index. This jump table is right here. It lists the basic block where you can jump to. Okay? So basic block 0 actually is here, and it does a -2. And basic block 8 perform A right shift 2. Okay? So it actually redirects you to these locations. However, if you look here, you can see that there is a range check. Okay? This range check means that the index variable is in a valid range. So no one can really attack this code. It is already safe. So in that case, the compiler can understand that it is safe, and instead of adding these end branch instructions, it adds a no track prefix before the indirect branch. So the CPU will not track this indirect branch. So now we reduced code size, and also we reduced the landing pads for the attacker. Another thing that we can do, as I said before, we can add the node CF check attribute in front of the function, and then we will not need the end branch instruction before. We can also use it for special functions. Let's assume I have a special function called execv. It's a very dangerous function, and I don't want anyone to jump to this function except for one or two or very specific indirect branches. So what I will do, I will tell him not to add the end branch instruction at the beginning of that function, and instead I will add the no track prefix for every location that is going to jump to this place. Of course, I will need to do some kind of a check to make sure that it jumps to the correct place. Another thing about legacy, we are enabling running this set enabled code with legacy code, meaning code that was not compiled with CET. In order to perform this, we set up this legacy code page bitmap. The operating system and the dynamic loader is responsible to create this bitmap. And we signal each page, we flag it. We say this page is CET enabled, this one is not CET enabled, and so on. So if we jump to a page that is not CET enabled, then we don't do any check. We can enable and disable this legacy interwalk. So this is the IBT, indirect branch tracking state machine. At the beginning, we are in the idle state. In the idle state, as long as we have any instruction that is not a branch instruction, indirect branch instruction, we stay in this idle state. However, if we have if we have a branch instruction that has no track prefix before it, we are not tracking it. If we do have indirect branch call or jump, then we move to the next stage. The next stage actually looks and checks that the next instruction is indirect branch. If it is indirect branch, then we are back to idle and we're good. If this is a legacy page, then we're also good. However, if this is not any of what I said before, and this is not an end branch instruction, then we are moving to the fault state, meaning we are raising an exception, control flow protection exception. There was no perceptible slowdown measured, and we did it using ICC compiler and ran spec 2006. The code size growth is about 0.41%, which is really low. Okay, I tried to summarize it by doing some kind of a security analysis to those two techniques. The first one, Shadowstack. So it enforces a function to return to its call site. You cannot return to anywhere else, just to the place where you executed the call instruction. It prevents pivoting the shadow stack. You cannot control this shadow stack. Why? Because you cannot control the shadow stack pointer. Okay, it's non-writable, and the page where the shadow stack resides in is also non-writable. So you cannot pivot the shadow stack. It prevents reusing old frames because we only have increased SSP. We don't have decreased SSP, so you cannot use old frames in the shadow stack. It keeps the stack ABI intact. For example, there are other solutions like SafeStack that change the ABI. In this case, we don't change the ABI. The ABI stays the same. There's no requirement for other tools like what I talked before about ASLR that try to randomize things. So other solutions may require ASLR that is already vulnerable. We know that. So in Shadowstack, we don't need such thing. It can be applied to full stack. You can run it you can compile using CET from kernel to application. It supports dynamic linking. Other solution, many other solutions don't support dynamic linking, and they require link time optimizations. So you don't have to do that. It's not limited to C and C++ programming languages. You can use any language that you want. And as I said, we have very low performance overhead. Indirect branch tracking. So it enforces you to jump back only to jump to places where you intended to jump, right? And we have an AIR metric, a little bit about AIR. AIR is an average indirect branch reduction that was introduced by Zhang and Arsekar that tried to quantify the fraction of possible indirect targets eliminated by the CFI technique. Meaning, how many indirect branches are still vulnerable or are now protected, okay? So, in our case, we are only vulnerable in 0.02% of the indirect branches. While if you compare it to LLVM CFI mechanisms that are already implemented in LLVM, then they are about 10 times more vulnerable than, according to AIR, than CET. So we have a very good security metric. It is very difficult to create a job attack and cop attack, because if you need to indirectly call and chain them together indirectly, then you need to be very smart about the stack and make sure that there's no return on the way, because once you return, you hit the Shadowstack protection and there is an exception. So it's really difficult to create this thing. However, if you want, you can still use software-based instrumentation to check for those 0.02%. So you can check that in those cases, you jumped to this target from a valid indirect branch. And as I said, there is very neglectable performance overhead. So what is the current status? LLVM already supports Shadowstack and indirect branch tracking, including optimizations, like in the case of switch case statements. It has two new switches, -M Shadowstack, -M IBT, that enables the corresponding technology. It has new instrumentation flag called -F control flow protection. It has two variants, return to instrument Shadowstack fixes, and branch to instrument and branch instructions. And you can, of course, do both. There's the new attribute, no CF check, is also inside the LLVM community. ICC and GCC compilers both already implemented CET and updated the corresponding libraries. You need also to change the linker and the operating system and the program loader and so on. Microsoft compiler is also being currently updated. What we'll have next? -M CET is a superset flag for those two, -M IBT and -M Shadowstack. This also will be in the future. A fix-up for set jump and long jump, the case that I showed before, is also being promoted into LLVM. LLVM linker will also be updated to support new ABI flags and generating IBT-enabled PLT. So we are back to the summary. What I presented today is the control flow enforcement technology, also known as CET. It introduces new hardware-based technology that try to implement CFI, control flow integrity mechanism. It uses two techniques, Shadowstack, separate stack, especially for control flow, and indirect branch tracking that uses end branch instruction in specific valid targets. Shadowstack protects against ROP attacks, return-oriented programming. Indirect branch tracking protects against jump and call-oriented programming attacks. And It has very low overhead. CET introduces competitive protection metric rates while maintaining very low performance overhead. Questions?
Any questions?
So is this solution only implemented for x86 CPUs, or are you planning to extend it with other CPUs? Because at least the alternative stack could work on all CPUs where you have a explicit link register, for example, for ARM, where your branch just stores the return address into the register, and you could spill it anywhere, not on a data state.
Can you repeat again what?
The question is your solution Intel CPUs only, or x86 CPUs only, or it will be also extended to other CPUs?
So I guess our technology, our architecture can also use a similar technology, I guess AMD also. But currently this is something that is developed for Intel processors. Intel didn't announce to which technology it's going to, when it's going to release it yet. But yes, it's going to be integrated currently to x86 CPUs.
Hi. How does this interact with Spectre and Meltdown mitigations? Okay,
so the current Spectre mitigation that was introduced by Google, I think, to LLVM, doesn't work very well with CET Shadowstack. And Intel is introducing a new mitigation that's even better performance-wise, that will handle it. Also, CET in the future could handle some of the variation of Spectre.
I'm assuming the end branch instruction is a barrier instruction in x86, right? It has to act as a barrier. Otherwise, you could, in an auto execution machine, you could be executing your call or a jump prior to executing your end branch instruction. So assuming it's a barrier instruction of some kind, what benchmarks did you run to say that performance overhead is very low?
So we used Spec 2006 to check that. And there were several more microprocessor-related benchmarks that we also ran.
So that particular instruction is not a barrier instruction? Because it's at the entry of every function, right? The end branch 64 and 32.
Right.
But if it acts as a barrier
so you have a
instruction,
global function,
you will not be able to execute, even if you do not have jumps, you will not be able to execute many instructions down the stream.
Right.
So that will be a barrier instruction. So if you have that instruction in every function, I would assume that you will hit some performance.
Yeah, so as I said, so it can increase the code size, but as we've seen in those simulators, we have some simulators based on CMIX and SDE that are actually they are public currently. According to these simulators, we see that there's no really performance hit.
Thanks for the presentation. You mentioned when the kernel is saving the safe stack pointers, there's a system of token. Can you elaborate on that? What are the tokens used for? How they are generated? By whom? For whom? I didn't quite get it. Sorry.
So
you said there's a system of token which is used when the kernel saves the safe stack. Am I correct or not on that?
Yeah, so are you talking about SafeStack or Shadowstack?
Shadowstack, sorry, excuse me.
Shadowstack, okay. Yeah. So you were asking about the optimizations on Shadowstack, right?
You said there was a token used by the kernel to save the stack, something like that, and you just say it and then you switch.
So. The operating system is responsible to do the switch between different shadow stacks. So you may have different shadow stack for each privilege level, and there is a special mechanism in the operating system which we trust create those shadow stacks. And those operations are atomically, and it uses token-based mechanism. I didn't explain it here because it's really it's part of complicated to go through it here. But there is everything about Shadowstack is public, so you can find it online. It explains very detailed how to perform these kind of things.
Any more questions? Well, in that case, let's give Oren a round of applause.
Thank you.